Hey, what's up, guys? Previously I made a small video about algebraic geometry and about the skins and the sheaf or something like that. And I previously learned like 1 years at the university. I learned 1 year 1 year algebraic geometry, and I'm very interested in this subject. So, but I mean, right? You took a course and then you write a homework. Maybe hard still, it still means some many details. So what I'm talking about, what I want is that I make my own video lecture, and maybe this video list will update very slowly. But I try to start from the varieties, and the next video list will go to skins. Okay, so this is my first video about varieties. Hope you guys subscribe to my channel. So I think the standard two textbook I think is very good. One is Hartshorne, one is algebraic geometry, one is called Veckel. Okay, Veckel start from schemes, and the Hartshorne start from the varieties. Okay, and I think varieties is like a good example of schemes. So I think my understanding is that you start from varieties and you try to you start from varieties and then you try to think some detail and some property of varieties, and you start from varieties and go to skins. Okay, but if you can also start with the skins, but you will be more abstractly because you need to introduce the sheaf and the spectrum, and you need to have more background like in the category or something. But variety, at least for variety, should be very simple. For the starting point, should be very simple. Okay, so let me just quickly introduce, make some few videos about varieties. Okay, first one I want to introduce is affine varieties. Okay, so idea is very simple. You start from K, which is algebraic close. Algebraically, why always forget how to spell this? Algebraically close. Okay, so usually example will be K choose to be complex number, and then you can define a Kn, which is usually called a finite space. Okay, as a set is very simple. You just basically just collect, let's say A1, A2 up to An, and each AI belongs to K. Go away. So you just simply just a K by K, K. End of it. So just the coordinate each. So this is called points, or sometimes called coordinates. When this is called a affine space. Okay, when n is 1, usually call it a affine line. So affine line is like the hydrogen atom in the Schrodinger equation or quantum mechanics. So it's like whenever you don't understand something, you start from affine line. Okay, so now we take A to be K of x1, xn. So this is the polynomial ring with variables, and okay, and so for example, if you take F to be A, this is commutative ring. If you take F to be A, you can define a so-called zero locus, zero z of F, which is you take point P belongs to a affine space such that F of P is 0. So this is called a zero locus. So simply speaking, just the 0 points of some polynomials. Okay, and more generally, so if you can take a subset, so just some subset of this polynomial ring, you can define a z of t is all the points belongs to a kn such that f of p is 0 for every f belongs to t. Okay, so it's very simple. You take some polynomials, and z of t just the set of all the zeros of that polynomials. Okay, and so for example, if you take t to be, let's say, f1, f2, fr, so this means that t is ideal generated by f1 to fr. So hopefully you know some background of commutative rings. Okay, so your z of t will be just p belongs to a kn, where f1p, f2p, up to fnp. Okay, so just the intersection of all the zeros. So you see it is very simple. Okay, so very simple definition is an algebraic set. So algebraic set is just a y belongs to a kn is called the algebraic set. It's called the algebraic set if there is a t subset of a k polynomials. So basically, y is a z of t. So simply speaking, is that just if you assess if you take the points, that point is just a set of the zero locus of some subset of the polynomial ring. This is called an algebraic set. Okay, so who cares the algebraic set? Okay, so this is a basic property. This property is very simple. So I don't. Let me just quickly say it. Okay, so the first one is that union of two algebraic set. Union of two algebraic set is algebraic set. Okay, and the second one is that the intersection. So the intersection of the algebraic set is also algebraic. So, but this is any number. Okay, so the proof. This is very simple. Hopefully you can see this. So let me define a T1, T2. If you take the T1, T2 are both the subset of the polynomial ring, then T1, T2 to be guessing T1, T2. T1 belongs to T1, T2 belongs to T2. So this product is a polynomial ring. Okay, so you can ask what is T1 and T2, the zero locus. So I mean, if z of T1, T2 z means 0, means that either T1 0 or either T2 is 0, right? Because if fg econ a is 0, means that f of 0 or g of a is 0. So this you can easily prove that. I think this is very trivial, so I don't want to prove it, but you can write down the detailed proof. So z T1, T2, right, is 0. I mean, this is trivial. Okay, so let me just still quickly give you a proof. Okay, so this is true. The proof is very simple, right? Because obviously that you can check that if P belongs to, let's say, if P belongs to T of Z1 or P belongs to T of Z2, that means that obviously that P will belongs to Z T1 times T2, right? Because every point either if for every polynomial in T1 vanishes at P, then the Z T1 T2 by definition will vanish. Okay. So, which we have proved that z of T1 union z of T2 is a subset of z of T1 T2. Okay, and if okay, now we need to check the other directions. The other direction is trivial, right? Because z belongs to z T1 T2. Then following this, then you prove that z p belongs to either z T1 or z T2. Basically trivial, just by definition. Okay, so so union of two algebraic sets is algebraic set, right? Because this is union, this is also algebraic set, right? Just subset product. Okay, and so what is intersection of this? Should be very simple, right? Because if you have the intersection, means that both, right? So both should be zeros. Okay. So obviously that this you can view this as T1 union T2. Okay. You take two polynomials and a set of polynomials and the union, then so the zero locus of the 0 point of this union will be both should be 0 by definition. Okay, so this is also trivial. Okay, now you can also see that if you take the arbitrary family, let's say for y alpha to be z of t alpha, then your z of the union of t alpha alpha will be the intersection of z of your z of union z of alpha will be the intersection of y alpha. Okay, so this is all algebraic set. Okay, notice that the whole space, right? The whole space A, K, N will also be the algebraic set, right? Because it's a zero locus of everything. If you put zero, if you put zero ideal or zero, that means that every point is by default zero. Okay. And the empty set is also Z, and you can take a zero locus of, like, say you take a point, like say 1. Okay. Or you take all the ideal generated by all or basically K of x1 of xn. You take all polynomial ring, all the polynomials, right? Then all the polynomial has no, there's no one point such that it will be the roots of all the polynomials. Okay, so combine the previous one and 2, then we get the famous so-called Zariski topology. Okay, so since their union of 2 is a algebraic set, their intersection of everything is also an algebraic set. So basically, Zariski topology, you just say that the algebraic set, we define algebraic set as a closed set, Okay, so we make AKN a new topology. So this new topology means that the closed set is defined to be the algebraic set. But this is called the Zariski topology. Okay. And so the open set will be the complement of algebraic set. And you can check the very simple example. Basically, you can check that this Zariski topology, this AKN is now Hausdorff based on this Zariski topology. Okay, so let's do a very simple example. If you take A to be K of X, okay, so and you basically affine line. So what is the closed set? What's the algebraic set of affine line? Okay, so you know, right? Because this is X, right? So you only have single variable. So any f of X by the non-zero f of X, if X is non-zero, and by definition, you will have by the fundamental theorem algebra, you will have X minus C1 up to X minus Cn. Okay, so this tells you that closed set will be a finite set, right? Okay. So also any finite set is closed, right? Because you take any finite set, you can form a polynomial that every point are zeros. But there's also another closed set, which is zero, right? You put zero as ideal, then this closed set becomes everything. Okay, so you have this is your AK1, then all these points are closed. Single points are closed, and the finite collection are closed. And also there is one closed set, which is everything. Okay, so these points are close, and these are all points. Okay. Okay, so now okay, so let me give you a definition. So non-empty y of a subset X is called irreducible. So now we need to make a connection between the zero locus and the polynomials. It's called irreducible. If y cannot be written as y1 union y2, such that y1 and y2 are proper, so y1 and y2 are proper. So proper means that y1 different from y2 different from y. And each of one of them is closed, and each one of which is closed. Each one of which is closed. Y. Simply speaking, I want to say it's y1 and y2 are closed. So if y is irreducible, means that you cannot write there's a two union of two closed sets. Proper. Okay. So yeah. Okay. So examples. A affine line is irreducible. Why? Why? Okay. Okay. The reason is that in a finite, right? The finite, the proper subset are finite. Okay. So proper subset are finite. Proper closed subset is finite. It's always finite. Okay, so so you can check that if you have this whole point is irreducible, right? Because you cannot this guy is infinite. If k is infinite, so let me just write down. So ak if k is infinite, then ak1 is infinite. But as a set, it's just k, right? But k cannot be written as two finite set. Union of two finite sets, which are two finite. Okay. By the way, notice that k is algebraic closed, so k must be infinite. So no, so this is the important thing. K is algebraic closed, so k must be infinite. So infinite set cannot be written as the two finite sets, right? So very simple. Okay, and another fact is that if y is irreducible subset of x, and then y closure of y is also. Okay, so this is a simple, so you can check by yourself. Okay, so definition called a affine variety. Affine variety is what? It's just an irreducible irreducible. Let me just write down the definition. The irreducible closed subset of a kn. Okay. Okay. And so this is called so affine variety, just irreducible closed subset of a kn. Simply speaking, is that irreducible the zeros of irreducible polynomials. Yeah, so set the zeros of irreducible polynomials. Okay. Now we can define open affine varieties. Sorry, it's now cosine affine variety to be the open subset of affine variety. Okay, so okay, so let me just, we also need to define a thing. Let's say you take subsets of a, k, n. You can ask what is the polynomial such that it will vanish on y. Okay, if y is a variety, if y is a, if, I mean y is algebraic, right? You definitely know there is a such thing, right? But we can always create it. There is a code I of y such as all the polynomials belongs to k of x1 xn and f of x1 xn is 0 for all x1 xn in y. Okay, so you take some points and then you ask what is the polynomial such that this polynomial will, what's a set of polynomials such that every polynomial will vanish on every point of this y. Okay, and okay, so obviously that obviously what? Obviously is that the original we have z map, which map the subset of A. So subset of this. Let me just do this. So now we have two space. Right, one is this, and the one is this. Okay, and then we have the map, which called the one. We have one obvious map is to take 0 locus, and the one is this, take I. Okay. So the subset of this will make the algebraic set. Right, you take any subsets. Okay, now you take I, right? You take I will make the subset of, so let's say this is subset. You take subset of K, we will map into the algebraic set. If you take subset of AKN, then you will get something, right? But notice that this IY is actually ideal. This is trivial, right? Because you take a constant, it is still 0. So you take any polynomials times this IY, then still become in IOY because still become 0. Okay, and the 2 addition 0. So obviously that it will give you ideal. Okay, so now we have a relation. between ideal and algebraic set. So we need to investigate such relation. Okay, and yeah, I think probably this is the good start. Let me just write down some, yeah, maybe there's for next video. Okay, hope you guys subscribe to our channel.